Log on, tune in, find out. Another good idea from Cambridge.
When dimensions goes to infinity. So I will just start by defining the maximal function. So let f be a function in L1 of the space Rn. Then the maximal function of f so there will be actually several maximal functions, but one possible variant is to take the following quantity. So for every point in Rn, so this mf will be a function which at point x is equal to the supremum over all the possible positive numbers R of the average of f over the cube of center x and radius r. So here, this is the cube, so x plus r times the unit ball of L infinity. So you just, for every point, you look at all average over all radius and you choose the supremum of this quantity. Okay? So if I want to insist that here I am taking cubes as averaging sets, I will just write this m cube f. And of course, you can define the same thing for any convex body instead of the cube. And I will just consider the case of the Euclidean ball. So similarly, m balls f of x. So the same thing with balls instead of cubes. So this is the Euclidean ball. Okay, so let me just draw a picture, say, in the one-dimensional case. So say this is my function f. So for every point, I have to look at the maximal mass that I can grasp among all intervals centered at this point. And you get something maybe like this. Yeah, trivially, the mf can never exceed f, just because you are taking averages, and it behaves like 1 over x at when x goes to infinity. So in particular, it is never in L1, this maximal function, because it's not integrable at infinity. But what is true is that you have a control on the volume of level sets of mf, which is reminiscent of the L1 property. So in other words, this function is in the weak L1 space, and this is the content of the Hardy Littlewood maximal inequality. So maximal inequality. So from 1930. So there is a constant which depends only on the dimension, so that the volume of level sets of the maximal function of some function is bounded by some. So this constant times the L1 norm of f over t. Okay, so this, you can rephrase it by saying that the operator m is continuous from L1 to weak L1. But I will just consider only this inequality. And the base constant C, so the smallest C of n, I will write it as the norm of this operator. So the norm of MF from L1 into weak L1. So this inequality is extremely interesting because this maximal operator controls many constructions in harmonic analysis, and the fact that this inequality holds with some constant C of n is very important. Now the dependence in n a priori could be less important, but still a natural question is whether this quantity here is bounded by some absolute constant or not. Because if so, you could hope that there is some infinite dimensional phenomenon that is behind. So I will talk about this. Is this function bounded in the case of cubes or in the case of balls? So this inequality is, well, it requires some work to prove. So the simplest way to do it, the textbook proof, is like is using Vitalis covering lemma. And in this case, you have a constant which behaves like exponential, like maybe 3 to the n or 2 to the n. So Vitalis covering lemma implies that C of n is bounded by some constant to the n. So another interest of this inequality is that there is something which is obvious, which is that, as I said, this function mf in supremum cannot exceed f. So this is completely obvious. But now, when you have these two inequalities, you can interpolate between them and get boundedness from LP into LP for every p strictly greater than 1. So by interpolation, this implies that for every p greater than 1 and for every f in LP of Rn, this function is bounded by some constant depending on n and on p times the LP norm of f. So here it's really the strong LP space. And this is a very important inequality. Okay, so what is known about the dependence in the dimension? So this, like the simplest way to prove the inequality gives some quite bad bound. So what is known? So I will distinguish the case of balls and cubes. And also the case of the L1 to weak L1 problem and the LP problem. Okay, this I didn't write, but this is the base constant here. I will write it, as you might guess, as the norm of M from LP into ILSET. Yes. So there is a very positive result, which is due to Stein, which is that for the case of Euclidean balls, in this case, this operator is bounded by some constant which depends only on P. So here it is the best that we can hope. This inequality holds with some constant, absolute constant, depending only on P, for every p of course it has to, it cannot, the constant must explode when p tends to 1 because it's not bounded from L1 into, from strong L1 into strong L1. So this is the best that you can hope. And it's natural to ask whether this can be extended to cubes or actually to any convex body. And this was shown to be true, but only partially, only for p large enough, for p larger than 3/2. So this is due to Bourgain and also independently to Carberry. So soon after, I don't remember the date, 1986. So of course here, every time you have some exponent in the family of LP space which is singled out like this, it's a bit mysterious. But what is known, what happens for p between 1 and 3/2 is unknown. So it's open. This is an important open problem. So I mean, what I meant is that it's not known whether this uniform bound, not depending on the dimension, is true for in this range of p. Okay, so it's not known also what happens here. We don't know. Well, I will comment about this, but we don't have such precise results. There is still some bound which depends on n, but which is better than this exponential bound. So here, in the case of cubes, there is a bound n log n due to Stein also and Stromberg. In the same period. Oops, yeah. And actually, I should say that this, I stated these results for cubes, but they are valid for any convex body. The positive results for cubes are also true for any convex body. And in the case of balls, just slightly better is known, also in the same paper. It's not n log n, but it is n. So this is what was the situation. And recently, there was an example by Aldaz who showed that for the case of cubes, this quantity is not bounded. It tends to n, it tends to infinity when n goes to infinity. So it's really very recent, not bounded. So this is precisely what I will comment about in my talk. So I will give you a proof of this result, which is slightly different from the original one, and which also gives, which is simpler, and which gives also the order of growth of this constant. What happens for the case of balls is also open. So open whether there is a universal bound. So yes, there are two big open problems. This one for cubes or any convex body for p between 1 and 3/2, and for balls in the case of L1 to weak L1. So I will just comment a little bit on the Stein-Stromberg argument. So how does this argument work? Just in what is the main idea behind it? Yeah.
The result of Aldaz is only for cubes?
Yeah, only for cubes. So I will show you in detail, and we will count integer points in cubes. So this is very, very specific to the cube. So I just put focus on balls and cubes because there's most natural families of convex bodies, but you may ask for L1 ball, for example. Like it's not known what happens. So about Stein-Stromberg argument. So where does this n log n come from? So the first, the hardest part is to show that if you don't take this supremum over all the possible radius, but only on a very lacunary sequence of radii, then you have a uniform bound. So if m, say m tilde, is a very lacunary version of m, so more precisely this one, you take the supremum over all radius which are powers of n, right? So 1, n, n squared, and so on. Also negative powers of the same quantity. Say it works for balls or cubes or any convex body. Then this is bounded. Because the radius are so different than if you take a ball or cube of radius n, and if you add it to a cube of radius 1, it's you almost did not change the cube volume-wise, say. So this is the first part of the argument. And then once you know this, if you want to control the whole range of radii, so what can you do? So first, you don't lose if you replace this continuous family of radius by a discrete one which is small enough so that the volume of two consecutive cubes are within a constant factor. So if you take, instead of all possible positive numbers, just powers of 1 plus 1 over n, then you only lose a constant factor. This is because the cube of radius 1, or the ball of radius 1 and the ball of radius 1 plus 1 over n, they have volume which is equal up to factor at most e. And now, once you have this whole family, you can just split it into n log n families which grow like this. This is by some union bound. This is bounded by n log n times n log n quantities similar to m tilde. Just because if you want to, n log n is the power that you have to raise this number to in order to get this one. Yeah, so just you split this family of radius, you split them into n log n families, and you use some union bound. So this is in a very sketchy way how the Stein-Stromberg argument work and where this n log n comes from. So this is really based only on volume growth. Now there is a recent paper by Assasnaor and Tirito where they show that the same bound of n log n is valid in a much more general framework, in the framework of metric measure space, which has some micro doubling property, which means that what we say that this factor basically did not change the volume this property holds. So let me write this now and tau. So with the same kind of argument, the same n log n upper bound is valid in a micro doubling so this means essentially that the volume of the ball of radius 1 plus 1 over n larger is comparable to the volume of the original ball, x. Okay? And they show that it is optimal in this category. So they construct metric space with this property, this volume growth property, for which the n log n bound is sharp. Plus, it is sharp. This category. So this means that if you want to improve of this n log n bound, you have to use more than volume growth in Rn. So I just wanted to say this. Okay, so now I will come to this lower bound in the case of cubes. But maybe before, I will just say a few words about the one-dimensional case, because already in one dimension, so cubes and balls, everything is the same in this case, but already in one dimension, the problem is really not obvious at all. So let me say a few words about this case. So first, instead of looking at functions in L1, it's equivalent to look at measures, because when you have a measure, you can always use a modifying argument to approximate by a sequence of L1 functions, and it's easy to show that this will not alter the value of the constant. So if you enlarge from L1 to measures, it does not change the value. If mu is a measure, positive measure on Rn, then the same inequality holds. So I just rewrite the definition, and mu is defined the same way. And then the inequality which was true for functions is also true for measures. So the volume of level set is bounded by the same thing as I defined before. Times mu. This is like a L1 norm of the measure. So it will be easier to look at direct masses basically than instead of L1 functions. And also it will be easier to look at a periodic version of the problem. So periodic version. If I have a measure which is one periodic on R, then of course it has infinite mass. So this is infinite, and this function also will be one periodic, and this will also be infinite. But you can just approximate by truncation and show that periodic measure will satisfy a periodic version of this inequality. So if mu, and I can write it even for n dimensions, if mu is a z to the n periodic measure.
In the first row there, the c plus 1, right?
Oh, sorry, yes. Yeah. Yeah, the norm of this operator from L1 to weak L1 is the same as the norm from measures to weak L1. So if mu is so invariant by the lattice translations, so of course then mu is also. And so I just like to look at what happens on one mesh of the lattice. So again, 1 over t times this norm times the measure of one mesh of the fundamental domain. So yes, right. Doesn't matter much, but just by if you have a periodic, you just by truncation, it's easy to see that this must hold. So now there is an obvious candidate for a lower bound from what could be the worst measure for the one-dimensional case. Just put direct masses at each integer point, and you may hope that this will be the worst possible measure. So a candidate for the one-dimensional worst measure, so the one which witness this constant here, just this one. Yes. So this is very easy to analyze. For this example, so what do I want to do? So I will just compute what is m mu for this measure, which is one direct mass at each integer point. So you fix a point, and you look at all intervals centered at this point, and you want to maximize the average number of integer points per unit volume. So if you are very close to an integer, then obviously you just have to take the smallest interval which contains exactly this integer. So this will show a behavior like 1 over x close to integer points. If you are in the middle of the interval, then your best choice is to take the interval of length 1, which contains both extreme points of the interval. And if the critical case appears here when you are at 1/3, because this interval here has length 2/3 and contains 1 point, and this one here has length 4/3 and contains 2 points. So this shows that the mu, which is something like this, is always greater than 3/2. And actually, this constant 3/2 works for this measure here. It's all level set are smaller than 3 over 2t. And once it was conjectured for some time that this 3/2 could be the exact value of the norm in the one-dimensional case. But it's not. It's a bit surprising. The constant in dimension 1 is not 3/2. It's slightly more. It's some algebraic number, 11 plus square root of 61 over 12. So it's slightly than 3/2. Yeah. And how do you construct measures which are better than this obvious choice? Well, it's not obvious. What Melas is doing is that given a measure, he has some procedure to improve it, and then he constructs a sequence of measures that converges to this constant. But it's not. After a few steps, it really becomes complicated and not obvious at all to see what happens. But still, the answer is known in the one-dimensional case. Okay, so now I will turn to the case of n dimensions, and I will. So there is also an obvious candidate for the n-dimensional case, which is the same as this one. just put direct masses at each point of the lattice z to the n. And actually, it is a counterexample. So it's really simple to think about this example, but it's really, you really have to be convinced that it will be a counterexample to work out the details and show that it is indeed it gives non-boundedness of the maximal function. So in Rn, an obvious candidate is to put the same thing, right? And Aldaz proved using this example that the quantity of interest tends to infinity, and I will show you that I will prove you this and also give a concrete bound. So this grows like log n basically. Yeah, so this is log n to the power 1 minus little lower 1. So any power, the exponent can be as close to 1 as you want.
Log n to some power or not?
Log n to power, okay, I will write it larger. Log n to the 1 So probably you can get 1 if you really go deep into the proof, but I don't. Or maybe it's log n over log n, or I don't know. I didn't really try to very far to prove precisely, but still there is a gap between this lower bound and the n log n bound upper bound from Stein-Stromberg. So it's still quite a big gap. Okay, so what will happen? Is that for this measure, the typical value of the maximal function will be large. So if you remember the inequality, yeah, it's written over there. I will actually look at values of t for which this quantity is, for example, half. So in other words, this will be the median of this, if I think of it as a function over the probability space, which is a unit cube, and the median will be of this order. Yes? So I will not look at tails, but really the typical value of the maximal function for counting integer points. We'll show that the median of, so I will just write explicitly what is this for this particular measure. So in this case, this amounts to counting integer points in cubes. So this is the measure of a cube for this measure mu over the volume. So this is a function on Rn, which is z to the n periodic, and the median of this function over the unit cube is larger than than this. Okay, so for example, just to see a few examples, if you start from a point which is a point from z to the n, then the best thing you have to do is to take a very small radius, and in this case the value of the function is plus infinity. Yes? But this, of course, will not be a typical point. So another, say, extreme case is the case of a point which is exactly in the center of some cube in z to the n. In this case, the best choice is to take the cube of radius 1/2. It has volume 1 and it contains 2 to the n points. So again, the value is large. Okay, another example is the point for which the coordinates are very well spread over 0 to 1. Yes, so this is far from both previous examples. And you can check that for this point, what you get is bounded by maybe by 4. Yeah, so this maybe does not indicate very much what happens for typical points, but it seems that maximal function is large for points which have coordinates which are clustered around some numbers, and is large for points which are coordinates which are well spread. And we will see that it is indeed the case. So maybe I should say that counting points in cubes is really very easy. Because how many points do you have in a cube of center R, X, and radius Y, and radius R, sorry. So you just have to look what happens for each coordinate and take the product over all these numbers. So it is product from I equals 1 to n of number of points into Z, number of integer points in the interval of center xi. So xi are the coordinates of x. So this is some interval of length 2r. So how many points from Z does it contain? Well, it can be either the lower integer part or the upper integer part of 2r. It depends on the value of xi. This is equal to either the floor or the ceiling of 2r, depending on of course, all this depends only on the coordinates modulo 1. Okay, maybe at this point it's good to show a picture of what happens for typical points. So I have some picture. So can you see it? It's okay. So I plotted this function here. So it's in logarithmic scale, the number of points per unit volume. And you see that, of course, each time the radius increases and grasps a new point, then it increases, and it increases by quite a lot because it's a whole face of the cube which brings many new points. Each time for some coordinates, when the radius grows, each time it grasps a new point, it grasps the whole face. So it tends to be like this. It decreases and it has some sudden increases for some points which are uniformly distributed over the unique interval. And also, it seems that this function is close to be periodic. If you switch from radius r to r plus 1, so small values will remain small and large values will remain large. So this is because if you switch from r to r plus 1 in this formula, it does not change which rounding you take. So it's large remain large and small remain small. And if you plot this for large dimensions, you see that it is even more true. So I plot it for n equals 20 and n equals 100. So maybe you can notice that this function, of course, it has to be equal to 0. So the log is equal to 0 each time that the edge length of the cube is an integer. Because when you take a cube with the edge length integer, whatever the center is, it contains exactly as many points as the volume, right? If you have a cube of radius 2 in 3 dimensions, it contains always 8 points, except if you are exactly on the boundary, but this will happen with probability 0. So this function is periodic and it vanishes at every half integer, because here is half the edge length. And when you see these pictures, you might think that the maximal will be attained from some value of r which is not too large, because in these pictures it happens between, say, 1 and 2. And actually this is false. You may have to go to values which are up to square root of n, but you cannot really see this on the picture, and the reason is that it's related to the law of the iterative logarithm, and log of 1000 is not so large, so you cannot really see what happens for really large n on this picture, and maybe that's the reason that it's really easy to look at this example and to be convinced that it's not a counterexample. You really have to look sharply at what happens to show that this function is typically unbounded. Okay, so I will now come to the analysis of the example. So I keep this formula. Okay, so for fixed parameter t, and I will say that a number xi from the unit interval is t-centered if it is in the central subinterval of length t. This is length t. And there is a simple calculation that is summarized in the following lemma. Well, it's only lemma. So if a point from the unit cube has many coordinates which are centered, then the maximal function will be large. This is basically the content of the lemma. So what is many? So many will be much more than expected. So I will write right after t centered coordinates, then the maximal function at this point, so this function here is large. So the expected number of t-centered coordinates, it will be nt, right? Because each coordinate is centered with probability t, and they are independent. Now the standard deviations will be square root of t times y minus t. So let me look at the case where the number of coordinates exceeds the mean by more than k standard deviations. Yeah, so in this case, the maximal function is large. This is larger than exponential k squared over 2.001. So this could be anything larger than 2. And this is true at least for large enough dimension. So n larger than constant times k squared over t 1 minus t. So it may look a bit technical, but really the proof is very simple. If you know that the point has many coordinates which are t-centered, then you know for which length of intervals you have to consider. So if you know that a point is between in this t-centered subinterval, then it's a good idea to look at, for example, this value of r, because if you take r equals 1 plus t over 2, you will be sure to get both 0 and 1. And you can look at this plus any integer number. It will be something good, because you will be in the upper rounding. So you just look at cubes of radius r equal some integer number plus 1 minus t over 2. So then you know that for each centered coordinates you take the upper rounding, for the other you take the lower rounding, and then you just optimize over n, over s. And the best choice is to take s of the order square root of n. So you really have to look at large cubes, even if the pictures don't really show this. Okay, so but this is a very unlikely event that a point has such many t-centered coordinates. Yes, the probability that a point has more than that number of centered coordinates this is given by the central limit theorem, right? You are doing Bernoulli trials and you have this many of successes. So this is like basically the probability that a Gaussian, normal Gaussian is larger than k. So it's like something like this. Yes? So here you see that we are not so bad, because if this product here had been larger than 1, then we could have concluded a lower bound on the maximal function. So it is not, it is less than 1, but it is quite a close fail. Now the point is that for fixed t, this is unlikely to happen. But if you consider the union of all possible values of t, then it will be a much more plausible event. Yes, so however, exist t so that this happen will be much larger. For fixed k, it tends to 1. So I will comment on this. So let me write it now. So here you can really think of the coordinates of x as random variables which are independent and uniformly distributed on the unit interval. So we just write capital Xi to fill the standard probability notation, but it's the same as the small xi as before. The independent random variables uniformly distributed on the unit interval, uniformly distributed on 0, 1, and define for every t, you can look at the best k that you can put in this formula. So for every t, define kn of t by requiring that among xi there is that number of variables which are centered, which are t-centered. Kn of t. Yeah, so this defines a random process for every indexed by a sequence of random processes indexed by t, by a time, one could say, between 0 and 1. And it's known what's happened at the limit. This process converges to a Brownian bridge. So this is a theorem by Donsker. The sequence of stochastic processes defined this way, or I will just multiply by convenience by this quantity. So this is a sequence indexed by n, and each element in the sequence is indexed by t. This converges towards the Brownian bridge. We call it beta t. Yes, so a Brownian bridge is a Brownian motion which is conditioned to be equal to 0 at time 1. So it resembles a lot this picture, by the way, right? It's like yes. So this is related to what is called in statistics the Kolmogorov-Smirnov statistics. So what do I mean by converge? Well, if you just look at finite dimensional marginal, so for you fixed a finite number of times, t1 up to tp, and then you say that this sequence of Gaussian vectors converge towards this one. So there is a covariance which is hidden in the definition of the Brownian bridge. If you just want this, it's really easy. It's just the multivariate central limit theorem. And this is only what is needed at the most elementary level. If you just want to prove that this family of measures is a counterexample to the fact that the maximal function will be bounded. So if you really want qualitative behavior, it's really easy. Now, if you want to be more quantitative, you have to say, so first, what it's true that it converges in the supremum norm. If you define this on the right, there are some issues of measurability which are hidden behind this. So you have to work with this cohort space and things like this. But once you have the right framework, it's known what is the speed of convergence. So it's a theorem by Komlos, Major, and Tusnadi that in the supremum norm, the speed of convergence is log n over square root of n. Yes, so for every n, there is a way to define on the same probability space both this sequence and the Brunel bridge in such a way that the supremum between them is always bounded by this constant, by this factor. So now you just have to translate this problem into another one which involves the Brunel bridge, and it will be much more flexible objects. So I will just finish. So we apply the lemma for some choice of t which will be random, for the best random choice of t. So you had some restrictions, so you cannot take all the intervals 0, 1. You have to be away from 0 and 1. So, for example, something like this will be safe. And then the typical value of the maximal function is larger than what was in the lemma, and k is the best choice, so it's the supremum over all t in this interval of this knt that was defined here. And now if you by this Komlos measure to study theorem, this will be almost the same if you replace this object by the limit object, if you write directly what happened for the Brunel bridge. So this will be almost the same that the supremum over t in the same interval so you have to divide by this. So this is the covariance of this is the variance of beta t. Yes, so you look at the supremum of Brunel bridge divided by its standard deviation over some interval which grows and which, when n increases, grows to the interval 0, 1. So there are several. Once you are in the probability framework, you really have a lot of freedom, because there are several transformations that relate, for example, the Brunel bridge and the Brunel motion. And for example, this is equivalent. This is the same law, which identical in law, identical in distribution, to another quantity which involves Brunel motion instead of Brunel bridge, which is maybe more familiar. So it's kind of change of time Yes, so this is really a usual Brownian motion. And now this is a more familiar setting, and this here is governed by the law of iterated logarithm. Yes, the supremum of the Brownian motion between 1 and a, so for a, when a tends to infinity, is equivalent to square root of 2 log a. Supremum. And you use the fact that the supremum of between t or u between 1 and a of bt over square root of t is equivalent yes, and this completes the proof. So just in 2 minutes, so this was very specific to the case of cubes, because we explicitly relied on the fact that it's very easy to count points in cubes. But is it true that the same examples is a counterexample for balls? Well, it's certainly much harder, but maybe not hopeless. So the question is, if you take a typical random point in 0, 1 to the n, when for n large, you look at all balls that are at this point, and you maximize the volume of number of points, of integer points per unit volume. Is it true that the typical, the median, say, of this random variable tends to infinity with n? So if so, it will disprove, it will show that the maximal function for balls is not bounded in the same way that it is not bounded for cubes. So I will stop here. Yeah, thank you.
Questions?
Could I ask what happens in the discrete case? I mean, if you consider the discrete hypercube, maximal functions, would that be studied? So instead of,
What do you mean?
well, you take 2 to the n instead of r to the n. 2 points to the n. And put on Hamming method.
Well, in this case, all points are the same, and there is only one. Yeah, it will be easy to. All points will be the same, so you have to do some calculation, but.
Even in little one, you know, in the norm is
The norm in L1.
no, on one side it's little one.
Yeah.
If you take, on the other side it's still capital.
Take the
one.
average. Give it to this one.
You want to relate it to the value of the function at only discrete points. So
Yeah,
you probably
yeah.
want it to be.
In other words, I mean, if you
little
consider
one.
r to the n, just the functions which,
Should
the measures
go
which are
f-
concentrated
You
on.
can look at it as an operator from little one of Zn to weak capital L1 of Rn, I think. Maybe. It's really just what happened to this operator when you restrict it to the span of the delta function.
Yes, yes.
I think that this is really I think that this is
Questions? Thank you again.